Welcome everyone to the Introduction to Basic Statistics in R workshop. My name is Pamela Reynolds and I'm the Associate Director here at the UC Davis DataLab for Data Science and Informatics. For those of you who haven't heard of DataLab, we're a program funded by the UC Davis Provost and supported by the library to facilitate the application of data science methods, technologies, and best practices to enhance research and learning in all domains across our university. We provide research services, including office hours, which you could check out on our website at datalab.ucdavis.edu, as well as provide research project support. And we also host training activities like this workshop that we're running today. Now, today's workshop is being offered by DataLab in conjunction with a wide array of workshops as part of UC Love Data Week. We'll post a link in the chat for you to check out the other training opportunities that are happening here at UC Davis and across all the UCs this week. I know there's only 2 days left, but there's still a lot of workshops happening. Now it's my pleasure to introduce our instructor today. Wesley Brooks is a data scientist here at DataLab. He has his PhD in statistics and has been programming in R for quite a while now. And this is our first time running this Intro to Basic Stats in R workshop. So we'll be asking for some feedback at the end of the workshop, and we really want to hear from you. Also, this is a two-parter. So just as a reminder, you've registered for today's session, and then we have another follow-up session, and you are automatically registered for that as well, where we'll continue to cover more material. So with that, I'm going to pass it over to Wesley and take it away.
All right, thank you, Pamela. Hello, everyone. It's great to see you all here. I am, as you are aware, here to talk to you about an introduction to basic statistics with R. So I think it would be helpful for the folks who can or wish to there is a read-along script that folks are going to be able to see a lot of what I'm doing, and I'm going to drop a link to that into the chat. Okay, so that includes a lot of text and code. I'm going to be sticking pretty well to the code that is in the document there. So I'm going to be pacing it at the pace of my typing. So those of you who want to code along in RStudio, which I think the background for the workshop indicated that you should have installed R and RStudio. If you want to do what I do as I do it, you should be able to keep up live with the work through the workshop. But for those who would prefer to simply listen along and absorb, the code is all there to be able to do it later at your leisure. Okay, so the title for this workshop includes, it is an introduction to basic statistics with R, and that includes both that it's an introduction and to basic statistics. So as you might guess, I'm not going to assume a particularly high level of familiarity with statistics in advance. That said, because we have a 2-hour workshop here, and then of course another one next week to introduce stuff that would ordinarily be done over a couple of quarters in a course. We are necessarily going to be gliding over some of the nitty-gritty details and keeping this at a fairly high level. And I want to maintain a focus on being able to do the work in R as opposed to doing much math, although there is inevitably a little bit of math in order to understand understand what the R functions actually do. So with that as background, let's begin. I'm going to share my screen and you'll be able to follow along with me if you wish. Okay, so it's going to be I think a great place to begin in terms of introducing basic statistics is to talk about some examples of the kinds of questions that motivate the material that I'm going to cover in the workshop. And doing this first step is also going to help confirm that your R environment is working. So for those of you who are following along, this will be an early check to make sure that there's not going to be any unpleasant surprises. The data that I'm going to be working with comes from an R package called FOSS data, FOS data, for free and open source data. It's an R package that is full of data sets from free and open source papers that have been published in journals. So there's a lot of good options there. If you want to install the package, you can then use R's help function to look at the details of each data set. However, for the purpose of this workshop, it's optional to install the package. For the most part, for everything that I'm going to present, we're going to be using these two data sets that I have split off and put onto the GitHub repository for this workshop. So the folks who want to access the data can download these particular data sets without having to install a couple of R packages to get there. Okay, so these are two data sets. The first one is mice pop. So in order to read the first data set in, I'm going to read.csv from a URL, which is https in the colon and slashes raw.github usercontent.com. /west-brooks/basic-stats/main/data/mice_pot.csv. And quotation mark, just make sure that looks right. It does. Run that command. Okay. All right. This is confirming that I actually did get the data, but that's not how I wanted to save it. I want to create a variable to save the data, run that command, and now I've got it. Now I've got this object called micepot, which contains that data. And rather than go through the entire URL for this second data set, which is the barnacles data set, I'm simply going to select and copy and paste that first line, but change the name of the object I'm creating to barnacles, change the name of the data set I'm downloading to barnacles.csv, and run it. And now I have both of the data sets. Okay, so the mice pot dataset contains data on an experiment that dosed 4 groups of mice with different levels of THC. There were a low, a medium, and a high dosage group, as well as a control group that did not get dosed with any THC. And some of the questions that statistical methods can help us answer relative to this data set are, were there differences in the typical amount of movement between mice in different groups? Was the average amount of movement by mice, or what was the average amount of movement by mice in the group that got the medium dose? And both of these questions can be approached in a very direct way that relates to the particular sample of data, which is kind of interesting and is called descriptive statistics. And so, for instance, I can look at what is the average amount of activity for the mice within each group relative to the control group. So that is using the with command, mice_pot. I want by, so %_of_act is the percent of activity for these mice. Group is a grouping variable, and I wish to calculate the mean. Okay, run that line. And you can see that in my R console, I get an average amount of movement for each of the 3 groups of mice. Like I say, this is kind of interesting. Obviously, these numbers are all different. One's 97.3, there's a 99.1, there's a 71 or 70.7 and a 100. So if you wanted to answer the question, is the average amount of body movement among the mice in the different groups different from each other, you might be tempted to just immediately say yes, because we measured the movement of the mice in the different groups and calculated the average, and look, all of the numbers are different. However, the data or the result numbers that you see in this R output are related only to this very particular sample of data. And when we're doing science, when we are trying to answer questions about the world, typically we are interested in questions that are a bit bigger than the particular sample of data that we have to hand. We want to do something called inference to a population, okay? And so in this case, the population from which this sample of mice is selected would be all of those mice which could potentially have been selected for the study, right? So when it comes to asking the question, is the average amount of movement by mice within the different groups different from each other? If we're trying to answer that question at the population level, it's no longer sufficient merely to look at the averages calculated here in the based on the sample. Okay, so because we don't see the data from the mice that weren't part of the study, we're going to rely on inference to reach conclusions that are conclusions about the population. And the way we do that is by using some theorems from mathematical statistics that can tell us about the distribution of the sample relative to the population. Okay, moving on, I want to calculate for the barnacles data set, what is the mean number of barnacles per square meter. And this is a data from a study of the Flower Gardens Bank Reef in the Gulf of Mexico. We see that within the sample, the average number of barnacles per square meter is 332. Okay. So we might, as statisticians or as scientists, be interested in asking questions like, is the average number of barnacles per square meter greater than 300? Well, clearly in the sample, that's yes, but when it comes to answering that question about the population, simply calculating the sample mean isn't going to cut it. We have to, once again, think about the distribution of the number of barnacles per square meter and use that distribution to make some inferences about the population. And in this case, the population would be the entire area of the Flower Gardens Bank Reef, which is the case if the samples were selected carefully in order to allow generalization. Okay, so I've been talking about samples and populations because those are fundamental concepts to statistics. A sample is a pretty easy thing to understand. The sample is the data that you have. It's the numbers that go into your calculations. But the population is something trickier. The population is not always even obvious, even to somebody who's thought very carefully about the study. The population is the units to which you're able to generalize your conclusions. If we're looking only at the sample means, then we're unable to generalize our conclusions any further than the particular sample. But if we can reach some conclusions about the distribution of the sample means, then we might be able to talk about some broader population. And what broader population? Well, like I say, for the barnacle data, that could be the entire Flower Gardens Bank Reef. But in order for that to be the case, the science has to be done correctly, and that happens before you're getting access to the data. So this is a pretty important concept, that the statistics, the stuff we do in R, can be extremely powerful, but the thought process has to begin long before the data gets into the computer. For instance, if all of the observations for the Flower Gardens Bank Reef, if all of the barnacle counts came from one single piece of the reef, it might not be possible to generalize beyond that piece of the reef. Or if those sample locations were chosen because it was observed that they had a lot of barnacles, then clearly making generalizations to the rest of the reef based upon those particular locations is going to lead you to wrong conclusions about the number of barnacles covering the rest of the reef. Okay, so random sampling is one really important tool, and a benefit of random sampling is that it helps ensure that any of the units that get put into randomization could potentially end up as sample units, and therefore you're going to be able to generalize your conclusions to all of those units that might have gotten put into, or all of the units that got into randomization. Okay. So, to talk again about the mice with the THC, population there would be all of the mice that might have been selected for use in the experiment. And I can't tell you how big that population is, because that is a function of what happened at the lab. Those could be very specific mice who are chosen non-randomly, or they could be very typical mice that are known to represent the entire species of mice. And again, that's some thinking that has to happen at the level, at a level before you collect data and it gets into your computer. Okay, and so just like as a food for thought type question, I wanted to ask, or I want to say, so non-random sampling tends to mean that the population to which you can generalize from your sample is quite limited. And you can think about, what sort of population do you think you could generalize about if we, for instance, took down the age of everybody in this workshop? Would that be something that could tell us about the average age of people in California, the average age of people at the UCs, or some larger or smaller group than either of those? Because clearly the people who are attending the workshop are not a random sample. Okay, clear enough? I guess if people want to use green check marks, this is a decent opportunity to do so. To say, oh, hey, I got it, I'm following. Okay, I'm seeing a few. Cool, cool. All right, with all of that said, we're going to begin our discussion of actual doing statistics in R with talk about probability distributions and quantiles and densities. Okay. Probability distributions, for those who don't know, are functions that divvy up probability among the possible outcomes of a random variable. Okay. Each distribution has some important features, such as density and quantile functions. And the workshop today is going to focus very heavily on the normal distribution. It's because it's the single most important distribution in everyday statistics, and we don't have a lot of time to talk about a broad range of other distributions. So we're going to focus very heavily on the normal, and it should become fairly clear why when we talk about mathematical statistics. All right, so to begin with, I would just like to show you the density curve of a normal random variable. I see that I have this already filled in. Okay. So this is also a figure that is already reproduced in the document that you may be looking at. But taking a sequence from -4 to 4, and plotting that as the line plot, and adding a vertical line at the population mean, which in this case is 0. Okay, so as you can see, this is a pretty familiar shape, I hope, to most people. Even if you've never studied statistics before, you might have heard of this as like the classic bell curve, a normal distribution. This is the standard normal density, and you will see it again and again and again. So it pays to get a little bit familiar with it. So a density plot, which this plot I'm showing you is called a density plot because if you select a sample from the distribution, most of the numbers in that sample will be from the part of the curve that has the greatest density. Right, so that represents density in terms of, you know, in the intuitive terms of density, it is where most of the samples are. So if I want to sample 20 numbers from a standard normal distribution, I might say that x equals r norm, and here we're seeing a new function, 20. And the r norm function is the function that is used to sample from a normal distribution. Right. Now let us look at the sample we just drew. Oh, excuse me. I want to look at the actual numbers. So I'm going to print x, and that reports the values of x out onto my R console. And I'd like you all to either look at the numbers you just sampled from your own distribution, which would be different from the sample that I drew, because again, we're each drawing our own samples, even though we're drawing them from the same population, which in this case, the standard normal distribution is representing the population. Here, this sample is something unique that I just created and probably there's never been this exact sample created before. All right, now looking through these numbers, I see that there's a pretty even split of positive and negative numbers, which makes sense considering that the density is clustered around 0. So positive and negative look to be equally likely. I see that the largest magnitude here look like these numbers, which are 1.29, 1.26. There's nothing particularly negative, or nothing greater than, or nothing less than -1. So all of the samples that I just drew are clustered within the densest part of this density. That's actually a little bit unusual. I can actually show these numbers a little bit more clearly if instead of just printing them, I round them to 2 decimal points. It's actually a little bit unusual that none of the samples come from any farther away from the center of this distribution, because we do 20 samples from this standard normal density, and that means we should see something that happens, we should expect to see something that would happen 1 time out of 20. And that's a 5% chance. And when you're dealing with a standard normal distribution, the sort of thing that's going to happen 5% of the time, or has a 1 in 20 chance of occurring, is that one of these numbers would be either greater than 2 or less than -2. So we expect to see one of those. We actually see 0 of those, but that's just the way it goes when it comes to taking an actual sample of data. Things don't always follow the exact shape of the population. That's what makes samples so important and different from populations. Okay. Yes, and just to reiterate, on average, for a standard normal density, one sample out of 20 will be either less than -2 or greater than +2. But that is on average over the population, and this sample has 0 of those. Okay, and now I want to illustrate that 5% chance by taking that same standard normal density and drawing or shading in some areas of the plot. Okay, so on my screen, I have just ran some code, which is also reproduced in the document online, and it shades an area underneath the density curve that adds up to a total of 5% probability. And from this, you can see, similar to what I was saying, that these lines are all, this shaded area is almost aligned with -2 and +2. So you'd expect one observation out of 20 to land within the shaded area. And then the interval between the shaded areas covers 95% of the probability mass. And that concept of an interval covering 95% of probability mass is going to be become quite important when we get a little further on in the workshop. Okay, so we have a sample taken from a standard normal density. We have plotted the, I'm sorry, we have printed out the sample. But let us also look at it in a slightly different way, which is the histogram. So I use the hist function to look at a histogram of X. Okay, so the histogram is the analog of the density curve, except the histogram corresponds to a particular sample as opposed to the population, which is represented by the density curve. Now I say it's an analog to the density curve, and yet, as we can all see, this particular histogram that I generated, and probably the histogram that you have generated on your computer using the random sample that you generated, looks nothing really like the standard normal density. Again, just to reiterate, what we are working with here is a particular sample that is generated from the population that is shown in this smooth standard normal density. And when you're working with a particular sample, it's never going to be an exact replication of the population. It's always a representative sample, but not a perfect mirror. Now, if I wanted to get a better representation of the population from which these samples are drawn, I could sample a larger number, or I could take a larger sample. So previously I took 20 numbers from a standard normal distribution. At this point, I would like to take 200 numbers from a standard normal distribution. So I am going to use the rnorm function, pass it the argument 200 to say draw 200 samples. And rather than look at 200 numbers, which is too many to really scan visually, I am going to again create a histogram now for this sample Y. Aha, so as the number of samples that I drew grew, the distribution of those samples begins to look quite a bit more like what we would expect from the entire population. Now, I have pointed out, a few times now that the histogram I'm presenting here represents a particular sample. It does not represent the population, which is defined by a standard normal random variable. However, it is possible for a number, or for a vector of numbers, a set of numbers, could also call it a list of numbers. That list can sometimes be a sample and sometimes be a population, all depending on the context. So in the context of having taken a sample from the standard normal distribution, these values Y, these 200 values, represent a sample. But if I then wish to do some study of these particular numbers that I've drawn, they can represent a population from which I draw another sample. Okay, so I'm going to take a sample of 20 numbers from Y. I'm going to call this Y2, say that this is a sample. Okay, so I'm introducing a new function here called sample. The first thing I pass in is what I am sampling from, that is Y, the variables I just selected. And then I need to say, what is the size I'm sampling? Size is 20. So I'm drawing 20 numbers from that. And to start with, I'm going to sample without replacement. Now I want to look at these 20 numbers that I just sampled out of Y. Okay. These are 20 numbers. This is a sample taken from what would be the population it represents, which is this vector Y, which I sampled a few minutes ago. So it is possible for the same numbers to be a sample in one context, but also the population from which you take a sample in another context. There's no contradiction there. It's all about what is the level to which I could generalize given this particular sample that I just drew. I would be able to generalize to this vector Y, which I earlier sampled, but not necessarily to that higher population, the overall standard normal distribution, which was the population from which Y was drawn. Okay. That said, I actually wanted to sample here a sample of 20 from X without replacement. So I'm going to create X2 and again, use the sample function. And I'm sampling from X this time. And replacement equals false. Okay. And you'll notice this time I am not specifying a size, and that's because the default, if a size is not specified, is to sample something equally as large as the population being sampled from. And when I created X, it was a sample of size 20. So X2 will now be a sample of size 20. And I want to compare that to what I see if I take a sample again from X, but this time with replacement equaling true. Okay. Now, some of you might have already figured out that X2 is just going to be a reordering of X. So that if I calculate any summary statistics, such as the mean, the standard deviation, the median, they will all be identical between X and X2. And that is because X2 was sampled from X to be the same size, and the sample's taken without replacement. What the without replacement means is once you've taken a number, once you've sampled a number from X, you don't put it back. So the only way to sample something of size X without replacing is to get all of the original numbers, even though they might be in different order. So the mean of X, I calculate that is 0.15, mean of X2, calculate that, it is 0.15. It's identical. On the other hand, if I look at the mean of X3, I get something different, 0.297. So when I sampled with replacement, it allows some of those samples to be selected more than once, some of those samples to be selected 0 times. Therefore, the X3 sample comes away representing X, but it's not the identical values. Okay. Clear enough to everyone? Can we see some check marks if people are happy with the pace and ready to move on, or red X's if you think that I need to give you some more time to catch up? Seeing some green, that's good. Yeah, okay. Then I will move on to talking about random variables and some calculations. Okay, so there's a calculation that I've done several times already, and that is the mean. But first, I just wanted to point out that a random variable is a term that I'm going to be using again and again in this workshop. And a random variable is an abstract way of talking about an observation from the population. So in terms of the study of the barnacles on the coral reef, the number of barnacles in a square meter for any particular sample, that's a random variable until it's observed. So when we're talking about it in the abstract, we say random variable. Once we actually go and measure that particular square of the reef, it's no longer a random variable. Now it's an observation. Now it's data. So evaluating a random variable is another, if you think, how to put it, there is an idea that statisticians are like trying to quantify everything and think only in terms of numbers instead of the real world. And this is an example of exactly that kind of thinking, where we don't talk about experiments or measurements or the necessary scientific infrastructure. You can talk about an entire the entire process that goes into selecting some data point, as measuring some data point as a random variable. And then once that random variable is observed, you have an observation. And that washes away all the distinctions that come in with actually doing science, with actually going out and collecting data in the real world. But it gives us a language that we can talk about without having to get too specific about the experiment we're discussing. We can talk about random variable this, random variable that, instead of the number of barnacles in grid cell C199 on the flower pot banks, etc. Okay, so we've realized some random variables, which is my way of saying that we have taken a normal distribution and used it to generate some random numbers. And now we can calculate some quantities. So one that I've calculated several times already is the mean. I'll just demonstrate it again. R has a built-in function mean. Mean is the average that everyone is probably quite familiar with. You sum up all of the numbers in your data set and divide by the number of data points. Median is something different, but it is also a way of calculating an average. This one, though, is you put all the numbers in order and then find the halfway point. So you can see that the median here is actually a bit lower or a bit less than the mean. No problem with that, no surprise there. Again, a real sample is going to look different from the idealized version of its population. Because in a standard normal distribution, both the mean and the median would be exactly 0. That's not the case when we have a particular sample. Okay. So when we are talking about the mean of that population, as opposed to the mean of a sample, the mean of the population has a special name in statistics, and that name is expectation or expected value. Okay, so a random variable has expectation, but data has the mean. Now, there's no R function that calculates expectation. Unlike, we have an R function that calculates the mean, but expectation is a function of a population, and we typically don't know about populations. Right? We are working as whatever we're doing when we're interacting with data, we're working with a sample. So we don't have an easy way in R to say, oh yeah, tell me about the population. So you can calculate the mean of any numbers that you can plug into R, but for this abstract thing we call the distribution, R doesn't know what to do, okay? So in terms of the expectation, that's something that human ingenuity has to deal with it. Okay, so for instance, when I mentioned earlier that depending on the context, a particular sample could be a sample from a population, or it could be the population that other samples are taken from. Well, if we have a list of numbers that quantify the population, then we are able to calculate the expectation. I'm going to give a demonstration of that. Okay, so I have this vector y, and I can calculate the mean of y. It is 200 numbers taken from a standard normal distribution. Okay, the mean of y is 0.09. If I were to treat y as the population from which I'm going to take additional samples, so I did that with y2. Remember that y2 was a subsample from y. Okay. The expected mean of y2 would be 0.094, but the actual realized mean of y2 is 0.16. Now I can generate a bunch of new samples like y. So I say, I'm going to create a new object called y_means. I'm going to say that it's going to be of length 50. And I'm going to write a for loop in R. So again, I'm introducing something new, which is for loops. Some of you may have seen this before, either in R or in other programming languages. For those of you who haven't, you will at least be able to replicate the code that I'm using here. And it's fairly simple, so hopefully you'd be able to follow along. The number I is going to go from 1 to 50. That's all that's happening here. And now I'm going to say that the ith entry of y_means is the mean of a new sample taken from y of size 50, and let's say with replacement. Okay. Now I can run that little bit of code. And again, remind you that because I know the population I'm sampling from, it's y, I can say that the expectation of all of these entries in y_means is the mean of y. It's 0.094. However, if I look at the actual values that I get, I am confident that none of them will be exactly equal to 0.094. Okay, so let's look at, and round these to let's round them to 2 decimal places is good enough. It's easier to glance at. Right. Okay, so once again, sample means do not necessarily, and in fact almost never do, exactly equal the expectation from the population. Okay. Right. And just another way of visualizing those same numbers, I can once again use a histogram, this time of y_means. And I can put, I'm going to annotate that histogram with a line, a vertical line at the mean value, the population mean here, or the expectation. I'm going to use line type 3, so it'll be a nice little dotted line. Okay, so you can see that the actual observed values did cluster around their expectation, but none of them actually equaled their expectation. That's typical, that's fine. There's nothing surprising there. Okay. All right, so I've looked at means, expectations, There's another extremely common function that we use in statistics, the standard deviation. Standard deviation is the square root of variance. So there is a one-to-one correspondence between the two. So if you know the variance, you can figure the standard deviation quite easily by taking the square root. If you know the standard deviation, you can square it and get the variance. But standard deviation comes about because there's a desire for some calculation to measure how far a typical sample is away from the mean. Okay, so the direct approach to doing that would be to calculate the mean, and then for each observation, you can calculate the difference between that observation and the mean, and then just take the average of those. But that, because of the way that's calculated, that kind of calculation would always equal exactly 0. Everything positive would be exactly balanced by a negative quantity there. So statisticians developed a convention in the early 20th century that the way to handle the way to calculate the typical difference between an observation and the sample mean is to square all of those differences, calculate their average, and then take the square root. Okay. Now, you don't have to remember all of that because it's all plugged into this simple little function called SD. So I can calculate the standard deviation of the barnacles per unit area. Right, the standard deviation is 273 barnacles per square meter, which is kind of a large standard deviation when you consider that the mean barnacles per square meter is 332. That's saying that even though the mean is 332, a typical observation is something like 273 away from that mean. So quite a lot of dispersal in those values. And maybe we can see that reflected if we generate the histogram of those barnacle counts per square meter. Barnacles with an S. Okay. Obviously, a very different kind of looking histogram. And you can see there are some very large values that are represented here. That is part of the reason why the standard deviation in this case is actually quite close to the mean. Okay. Anyway, moving on, we can also calculate the standard deviation, or I guess in this case, I wanted to calculate the variance of the body motion percentage for mice who got the medium dose of THC. So that's the variance function, and I'm going to subset the mice pot data. So percent of act is the percent of activity by these particular mice, but I wish to only look at the subset of mice who got the medium dose of THC. Therefore, in the square brackets, I'm going to put a condition, which is that mice underscore pot group equals 1, which is the medium dose. Okay. Variance of that data, 689. Variance is actually not a particularly intuitive number, so we might look at the SD and standard deviation of those numbers rather than retype that whole argument. I'll just copy paste it. Or, like I said, I could just go to this variance, wrap it in square root. This is just to prove to you that, in fact, calculating the standard deviation or taking the square root of variance leads you to the exact same number. There is a one-to-one correspondence between the two. Okay, so for a normal distribution, we've talked about expectation, we've talked about standard deviation. I've been referring to this thing I'm calling the standard normal distribution pretty frequently thus far. Standard normal distribution is a normal distribution where the expectation is 0 and the standard deviation is 1. a standard deviation is 1, then the variance is also 1. It's a nice, convenient distribution that gets used all the time, but it is far from the only normal distribution. So I just want to show you all that that you can generate anything from the family of normal distributions in R by using the mean and SD functions of the normal distribution functions. You can use the mean and SD arguments, excuse me, to the normal distribution functions and just in order to give you a visual indication of what the densities for those other normal distributions look like. I have pre-written this code. It is in that web document that you may have access to, or that you do have access to and may be looking at. So you could copy it from there. I've also already produced this image in that document. But you see, these are all normal distributions. They all have roughly the same shape. It's just that some of them have been changed in location, and that's the expectation parameter known as mu. Some of them have been changed in width, and that is due to the standard deviation parameter known as sigma. Okay. Right. So to wrap up this this section on probability and distributions and quantiles and densities, I want to show you some of the functions that R has built in for working with quantiles, densities, samples, and probabilities. Okay, so I've already shown dnorm and rnorm. These are functions that calculate, in dnorm's case, a density from a normal distribution. And again, this plot that I have represented on screen now is a plot of several densities. So you can see that, for instance, the standard normal distribution at t equals 0, it evaluates to something slightly less than 0.5, maybe 0.4. So I say dnorm dnorm of 0. Evaluate that. Yeah, it evaluates to roughly 0.4. Okay. The density function is not something that you're going to use very often, so I'll move on pretty quickly. I've also demonstrated rnorm. Rnorm is a function for actually taking samples from one of these distributions. And I have typically been sampling from standard normal distribution, but it is certainly feasible to sample from a normal distribution that has a different mean. So mean equals, let's say 4. And we can also specify a new standard deviation. Let's say it is 0.5. So we should see these observations clustered pretty closely around 4. Oh, and I rounded to 0 decimal points. Okay, there we go, that's better. Okay, so rnorm used for actually generating samples in R. Qnorm is the one that I want to spend some time with right now, and that is the quantile function of the normal distribution. Now, quantiles are important because they map the range 0 to 1, which is the range of probabilities, back to the range of possible values for the distribution. And it's by evaluating quantiles that we're able to answer questions like, what is the critical point such that a standard normal random variable is less than that point 95% of the time? Okay, if I wanted to answer that, I would evaluate the 0.95 quantile of a standard normal random variable. Boom, it is 1.64. This is telling me that if I take a standard normal random variable at random, I guess that's redundant. If I evaluate a standard normal random variable, I have a 95% chance that the value it takes will be less than 1.64. Let's say I wanted to know kind of the converse, the number that if what is the critical value so that 95% of the time, if I evaluate a standard normal random variable, it's going to be greater than that point? Well, I can plug in qnorm. Now, the quantile by default looks at the lower side of the distribution. So I can say if it's above, if I'm looking above the critical point to have, or looking for there to be 95% of the mass above the critical point, then by extension, there must be 5% of the mass below that critical point. So subtract 0.95 from 1, and lo, we get that critical point is negative 1.64, because all of these normal distributions are symmetrical. And in particular, the standard normal distribution is symmetrical around 0. So we can evaluate some other quantiles, like for instance, what is the point where 50% of the probability is above that critical point and 50% of the probability is below? That's the 0.5 quantile, and it's 0. That is, half of the probability of a standard normal distribution falls below 0, half of the probability falls above. Okay. And finally, one last important function of the quantile, use of the quantile function, excuse me, is to calculate an interval that contains the evaluation of a random variable, say 95% of the time. So if there's an interval that contains the variable 95% of the time, that means that 5% of the time the variable is outside of that interval. And if I'm going to center that interval, then that says that half of that 5% is below and half of that 5% is above the interval. So I use the qnorm function again to calculate 0.05, the quantile of 0.05 divided by 2, and the quantile of 1 minus 0.05 over 2. And again, these are, one is the negative of the other, but it's negative 1.96 and 1.96. That establishes the interval that I showed you earlier, the shaded area. In the interval between the shaded areas lies 95% of the probability mass. And we've just confirmed that by using the quantile function, that this point here, negative 1.96, is the 2.5% quantile of this density. This point here, positive 1.96, is the 97.5 quantile, 97.5 percentile of this distribution. Okay. And I can actually simplify this a bit by combining those two lines into one. I just want to show that because it will come up a little bit later. Have 0.05 over 2, comma, right? The C function in R concatenates numbers together and turns them into a vector. So what I've done here is just called the qnorm function twice on one line, which, yeah, that's fine. Okay, so I had, a histogram of the y-means here, and I could actually put the, I could put quantiles of this. Oh, right. Got ahead of myself here. The functions I just showed you, the qnorm function, and there is also a similar quantile function for all of the named distributions in R. That works with a named distribution, but if you are working with a vector of numbers, like the way we did when we subsampled from the vector y, then there is a different function that R provides to evaluate quantiles. So remember, I'm just going to regenerate my histogram of the numbers y. Let's call it y means. Same one. Now, I can use the quantile function to evaluate the, let's say, the 0.1 and 0.9 quantiles of y means, that being the 10th and 90th percentile. So quantile y means, comma, 0.1. Okay, so the 0.1 quantile of y means is negative 0.08. And let me put that on the histogram. I'm going to copy paste that quantile function to save a tiny bit of time. Forgot to say that that should be V for vertical line. Okay, so that quantile is telling us that 10% of the probability mass falls to the left of that line, which by eyeball looks about right. And I can do something similar with a 90% quantile, or a 90 percentile, or a 0.9 quantile. So I copy paste that line, change the 0.1 to a 0.9, and I get this vertical line drawn here where 10% of the probability mass of this histogram is greater than this point. And therefore, if 10% is less than the lower line and 10% is greater than the upper line, then we have an interval between these two dashed lines that contains 80% of the probability mass of this histogram. Okay, so just wanted to demonstrate the quantile function, which is used to generate quantiles from a list of numbers, as opposed to the Q-norm function, which is used to generate the quantiles from a normal distribution. Okay, so the distribution function is quite a bit less important, I think. So I'm going to sort of breeze through it. I just want to generate the plot. Distribution function is an inverse of the quantile function. And with the distribution function, you are looking at, you're able to evaluate from a point in the domain of a distribution to how much probability is how much probability mass is less than that point. So I've annotated this plot with the same 95% interval. And you can see that this first, the first annotation shows that at about -2, we have roughly 2.5% of the probability mass is less than, is found values less than 2, while at +2, 97.5% of the probability mass is found at values less than +2. Okay, so this is the distribution function. It's not going to be as frequently used by most people. So I'm going to, continue on from there. Right, okay. So what is kind of important is being able to calculate the distribution function of a vector of numbers. So in this case, what is the proportion, if I want to calculate the proportion of entries into the vector y, which are less than or equal to -2, I do that using the mean function. And this is the equivalent to the distribution function for the normal curve, except now it's being applied to a particular known set of numbers. So I calculate the mean that y is less than or equal to -2. And that tells me that 2% of the y's are less than or equal to -2. I can also calculate the proportion of y variables that are less than or equal to +2. and that is 97. So even though the y's just represent a sample from the standard normal distribution, we actually come out with pretty similar quantile and distribution function results. So that is what I want to talk about in terms of probability and distributions. And I think it's time for like a quick bio break and a chance for people to catch up or take a rest or ask questions in the chat. While you do that, I've put a couple of food for thought type questions in the document, the read along document. I am also encouraging you to attempt or to play around with the distribution functions of distributions other than normal. And I've given a couple examples there. And when the two questions that I've listed here are what is the probability that a sample from the normal distribution with expectation 1 and standard deviation 3 is less than 0? And then for the sample y, what is the interval that contains 80% of the values? Okay, so either use the bathroom, get a drink of water, ask questions in chat, or just think about those questions. And let's be back here at 11:15 to continue. Okay, recording's back on. Just before we continue on, I was going to give a quick answer to those questions that I posed. Probability that a sample from the normal distribution with mean 1, standard deviation 3 is less than 0. That calls for the distribution function. So it'd be p norm of 0, where mean is equal to 1 and standard deviation is equal to 3. Boom. It immediately spits out the probability that I asked, and it's 37%. The other question was, for that sample y, what is an interval that contains 80% of the values? Well, we got halfway there earlier. I'll just run that calculation again. Yes. Run that calculation again, and it is quantiles of y, and I want the 0.1 quantile and the 0.9 quantile. So this is the interval. It's negative 1.24 to positive 1.40. The 80% of the probability mass for samples from y would fall within that interval. Okay. So we are going to begin and go through a quick discussion of mathematical statistics. I'm not going to belabor these points, and I'm not going to get deeply into the math here, but we need to look at some of the math that allows us to work with random variables in order to reason about their distributions. And that begins with some important identities that are used constantly when you're doing algebra with random variables. And in particular, the one thing I'm going to focus on is how do these identities relate to the mean? And that's because the mean has special properties. The mean is going to get used over and over again. And you've seen already in this workshop, I've calculated like, at least a dozen means, always looking at the means of data. And we do that because the mean has special properties. So one thing that I wanted to show in that previous section was that if you have a known distribution, it's fairly simple to use the quantile function to generate intervals where you know that interval contains some percentage of samples from the distribution. So looking at creating an interval from a normal distribution where 95% of samples would fall within the interval. Pretty simple to do using the quantile function if you know the distribution from which you're drawing the samples. But of course, in real life, when you have data from an experiment, data from some sort of observations, you almost never know what is the population from which those samples arose. We have to do all of our thinking about the population just based on the samples that we're able to read and put into our computers. But it turns out that the distribution of the sample mean actually begins to look a lot like the normal distribution as the sample size increases. And in fact, we can determine what normal distribution that what normal distribution is followed by the sample mean. And therefore, once we've collected some data, we're able to determine the distribution of the sample mean. We can do all that sort of thinking we were talking about when we went over distributions. We can do the sort of thinking that allows us to identify intervals into which the data will fall a certain proportion of the time, or critical points such that below that point, the data is likely to take the values only a certain proportion of the time. We can do that reasoning on this assumed distribution of the sample mean, and we use that to draw conclusions. And so in order to get to that point, we do need to go through a little bit of math, some identities, and look at how they relate to the mean. Okay, so in the document to read along to, I've put up 4 identities having to do with expectations and variances. Expectations are linear, so like the expected value of some constant times of random variable is that constant times the expectation of the random variable. And if you have 2 random variables, their sum, the expectation of their sum is the sum of their expectations. The variances are not linear because the variance of a constant times a random variable is a constant squared times the random variable. But we are able to say that for independent random variables, the variance of the sum is equal to the sum of the variances. And all of that matters because when you're calculating the mean, what you're doing is you are adding up random variables and multiplying them by a constant, or dividing them by n. But multiplication and division are sort of 2 sides of the same coin, so the same rules apply. As a result, I've shown in the read-along document that the expectation of a mean is equal to the expectation of the random variables in the mean, assuming they share the same mean. So like they came from the same population, and we're trying to figure out what does that population mean. In addition, variances work out so that as you're calculating the mean, the variance of that sample mean gets smaller as the sample size increases. So the variance of a sample mean is equal to the variance of an individual component of that, or an individual data point divided by the sample size. And as a result of that second property relating to variances, the sample mean has a distribution which gets more precise as the amount of data you're able to collect gets larger. Okay, so I'm going to illustrate that by creating a random variable, which I'm going to call capital X. Okay, and it's going to have mean -3 and standard deviation 3. So I'm going to say that X is a function that n equals 10, mean equals -3, and standard deviation equals 3. Okay, and that function just evaluates to sample some normal random variables with n mean equal mean and SD equal SD. Okay, why did I do that? It's because I can now just evaluate that random variable X, and I get 10 values out. Okay, so in particular, I'm going to create a new lowercase x to be the evaluated values coming out of capital X. And now I can show a histogram of those 10 values I just sampled. Now there's quite a large spread. You can see this histogram represents values that go from -5 up to +2. And in fact, I want to increase my sample size to be 20, not just 10. So now we've actually got an even wider spread from -10 to +4. Okay, and now I'm going to annotate this histogram with the 0.12 and 0.88 quantiles. Those are sort of randomly chosen points just because I don't want to repeat the 95% and the 95% intervals so often that you come to think that that's all that quantiles are good for. So here I can create a vertical line at the 0.12 quantile. And I can create another vertical line at the 0.88 quantile. M should have been a comma. Okay. Now, I can, instead of generating a single sample of this random variable X, I can do something where I iterate 50 times, generating that sample and calculating its mean. Okay, so I'm going to create a new variable, which I call mean underscore X. I'm going to say that it is numeric and it has size 50. Then I'm going to write another for loop. And in particular, in this for loop, I'm going to say mean X, the ith entry is equal to mean of, and then evaluate the random variable again with n equals 20. Okay. So let me run those lines. Okay, so now instead of looking at a sample of 20 variables from the 20, or looking at the histogram of 20 samples of X, I can look at a histogram of 50 samples of X bar, or the sample mean of X. Okay, so that is hist mean underscore X. Now we can see, even just glancing at the scales, instead of the scale being from -10 to +4, this is a much tighter scale from -4 to -1. So the precision, remember, these random variables were generated with an actual expectation of -3.0. So the probability mass is clustering around that population mean as I take more samples of the mean and calculate their average. Or I take more samples from X and calculate the mean of each of those. And just to complete the set, I'm going to copy this vertical line code. But I'm going to write a one-liner that creates both vertical lines here to show the annotations of the quantiles. Excuse me, that should be mean underscore X. Better. Okay, so now 80% of the mass of those samples is clustered between -3.5 and -2.3, as opposed to before when it was between 1.5 and -5. Again, as I calculate the mean, or by calculating the mean, I cause more of the probability density to cluster around the population mean. So means are special. Okay, so I have another plot to show you something quite similar. And I've already got the code here. It's pre-entered because I don't want to type this all out, but you can copy and paste it from the read along document, or just look at the figure that is presented there. However, I would suggest that you copy and paste that code and generate your own figure because it is random. So the results you see are not going to be exactly what are produced in that read along. Okay, so what I've done here is use the same population for all of these numbers. Every time I pass, or every one of these dots represents the mean of a sample that was drawn from a standard normal distribution. So I've added a dashed line at 0 because that is the population mean. Okay. What makes each of these dots different is that the x-axis is the sample size. So you can see with these observations here to the left of the plot, the sample size is quite small. It might be 1, 2, 4, 8. Okay, and you also see that there is quite a lot of distance between those observations and the population mean. But there is this consistent trend as the sample size that I am able to put into each of those means gets larger. The means that I calculate after taking a sample are tending to get quite a bit closer to the population mean. And that tendency is has been studied, and it's called by statisticians the law of large numbers. Now, law of large numbers is super important, but there is another related result in mathematical statistics that is, I guess, the most important theorem in statistics, and that's the central limit theorem. This is the one that actually tells us, okay, for pretty much any independent data, if you calculate the mean of your data, its distribution will resemble a normal distribution more and more as the sample size increases. Or to put it more simply, as the sample size increases, a sample mean tends to resemble, or a sample mean tends to a normal distribution. So I've written that symbolically in the read along document. And I've also introduced there this common notation where a sample mean, the mean of a random variable is capital X bar, and then the mean of a sample is little x bar. Now, the idea that the sample mean is tending to a normal distribution is true, but actually if your original data is from a normal distribution, then it's not a tending to at all. It's an exact relationship that the distribution of your sample mean in that case will be exactly normal. And it has this form where subtract the mean and divide by the standard deviation over square root of the sample size. But while that's a really nice result because you do that calculation and you can say that the quantity is getting closer and closer to a standard normal distribution, it relies on both the population mean and the population standard deviation, neither of which is known. So that's not great. Typically, we use the central limit theorem because we are doing some sort of inference on the population mean. So it's okay that the population mean is just a symbol. We're actually trying to say, okay, can we put bounds around that symbol? But it's complicated if we have two unknowns in that same equation, because then we're not bounding a particular parameter, we're bounding some combination of parameters, and who knows what that might be. So what we want to do is take the population standard deviation out of there and replace it with something we can just calculate from the data, the sample standard deviation. And we can do that. I mean, that's the first thing your mind might jump to, and it is definitely possible. And there's only one downside, which is that no longer does your quantity then go to a normal distribution. Instead, it tends to converge to this thing called a t-distribution. The t-distribution is quite a lot like a normal distribution, except that because you're estimating not only the mean, but also the standard deviation, there's more uncertainty in that estimation. That is to say, the distribution gets spread out and the tails of the distribution become heavier. And so I've got an illustration of a standard normal density in this plot. That is the dashed line, as well as the density of a t-distribution where, I've said this t-distribution has 5 degrees of freedom. You can see that near the center of mass, the t-distribution is less dense. And then in the tails of the probability mass, the t-distribution has thicker tails. So this t-distribution is something that comes up again and again when we're actually talking about using a sample of data to try and make some statement about the mean of the population from which it was sampled. Okay. Now, just to motivate this idea of the central limit theorem, that no matter, or almost no matter what distribution your data comes from, that if you collect your data, calculate the mean, that mean will come from something like a normal distribution. In order to motivate that a little more intuitively, we're just going to generate some plots. We're going to generate some data not from a normal distribution, and then see that, yes, the mean of those samples does tend to look like a normal distribution. Okay, so to begin, I'm going to generate 20 samples here from a uniform distribution. I'm just going to call these samples U. And sample from a uniform distribution, it's again the R part because we're sampling, and then unif. And I want 20 samples. Okay. Now I can look at the histogram of those 20 samples. Now the uniform distribution is a distribution that has a constant amount of probability density between 0 and 1. And so you can see that there is a pretty constant distribution of data between 0 and 1. Right? Now, what if instead of just taking a sample from that distribution, I take a bunch of samples from that distribution and calculate the mean of each? So I'm going to create some new variable called mean mu, and it's going to be numeric. I'm going to say there are 100 of them. Then I'm going to, again, put in a for loop. So I is going to go from 1 to 100. And each time we pass through here, I'm going to fill in a value of mean mu equal to the mean of 20 samples from that uniform distribution. And then I'll look at the histogram of that result. Okay, so now we're seeing something that looks quite a bit more like the normal density, with mass clustered in the center and sort of tailing away on both sides. If I were to go from 100 to 1,000 samples, we ought to see more detail in the resulting histogram. And you can imagine continuing to increase the number of means that you're going to calculate in order to increase the amount of detail that you would see in this histogram. Okay. going to move to the section now of the read-along document that's titled Events and Intervals. And so if you're following along, that's where we are. And okay, so answering realistic questions about scientific data is frequently a matter of evaluating the probability of some event. And by realistic questions, I mean the kind of questions that I introduced right at the top, like what is an interval in which we have 95% confidence that the population mean of barnacles per square meter falls in the interval. Or questions like, is there on average any difference in the amount of movement between the groups of mice who got dosed with different levels of THC? Evaluating those questions in a statistical way is going to boil down to working out some event and evaluating the probability of that event. Okay, so just to begin with, I want to introduce you to the quantile and distribution functions of the t-distribution, which are slightly different than the standard normal. So for t probability, I'm going to say pt. So let's say the probability that t is less than -1, where t has 8 degrees of freedom. So whereas with the standard normal random variable, in order to evaluate quantiles and the distribution function or the density, all we needed to know was the critical point or the number of samples or the quantile we wanted to evaluate. With the t-distribution, we also have to specify the degrees of freedom, which the degrees of freedom in the sort of data I'm talking about so far is always going to be the sample size -1. Okay, so this for using 8 degrees of freedom would be appropriate if we had something with sample size 9. If I want to evaluate the quantiles, okay, so there's a 17% probability that the t random variable with 8 degrees of freedom will be less than -1. So if I want to then say, well, okay, what is the quantile for t random variable that establishes the critical point where 17, so 0.17% of the probability mass lies less than that point. So I'm evaluating the 0.17 quantile. Again, degrees of freedom is 8. This should come out to be something like -1, as it's the inverse of the distribution function. And yeah, it's not exactly -1, but it's within a rounding error. And now, for instance, we can use the t quantile to say, if we know that some function of the data or some function of the mean follows a t-distribution with 8 degrees of freedom, what is the interval in which that mean will evaluate, say, 90% of the time? Then we're going to calculate the, so 90% of the time, that's, so 1 minus 0.9, let's see, 1 minus 0.9 is 0.1, divide that by 2, you get 0.05. And then the other side of that interval will be, 0.95. So 90% of the probability mass would fall between these two quantiles, 5% below, 5% above. And again, we're going to specify 8 degrees of freedom. And we get that that interval is from minus 1.86 to positive 1.86. Okay. So taking those critical points of the t-distribution, if you'll look back at the read-along document, I've illustrated how we go from an event to evaluating its probability to coming up with what we call a 90% confidence interval. Okay, the way we do that is we say that the sample mean minus the population mean divided by this s over square root of 9, or square root of n, which is s over the square root of the sample size. That's the thing that we know follows a t distribution with 8 degrees of freedom. So we have evaluated the interval that contains that t random variable 90% of the time. And so I've written a statement that has 2 inequalities in it, and it basically, or it is what we would call an event. This can either be true or not true, that the sample mean minus the population mean divided by the standard deviation over the square root of sample size, that is either between minus 1.86 or it is not between 1.86 and minus 1.86. Okay, so that is an event. That event is unchanged if we do some algebra, like multiplying both sides by s, dividing both sides by square root of n, and then subtracting x bar. We can manipulate that event to say that, okay, that is the same event as saying that mu, the population mean, is contained between the x bar, contained between the lower end of that interval and the upper end of that interval, which I've written out in the read-along document. And we know that event occurs 90% of the time in this setting. So if you evaluate this interval, replacing x bar with the actual sample mean, replacing s with the actual sample standard deviation, you get the 90% confidence interval for the population mean. But it's important to recognize what that means in terms of 90% confidence. This is an event. It can either happen or it doesn't happen. The population mean, mu, is fixed. It doesn't change. So when we say the probability that this event occurs is 90%, that 90% comes from the idea that we would have repeated runs of the whole experiment. That is, you would go back, repeat the entire experiment from the start, generate new data, plug that data into the same formula, and calculate a new confidence interval. And do that again with an entire new run of the experiment, and again with an entire new run of the experiment, each time calculating a confidence interval. 90% of those confidence intervals will contain this true parameter value. So it's not the same as saying that the probability that the parameter is in that interval is 90%. What's random here are the data. So the way you have to think about the probability is that you go back and you get new data, and you can average over all of those repeated operations of getting new data and rerunning the entire experiment. Okay. So I guess I'd once again like to see people hit the green check mark if you are keeping up and you're ready for me to move on, or you can hit the red X if you want me to slow down and think. Yeah, just let us know how it's going out there in workshop land. Okay, so I'm seeing a bunch of green. That's good. People are ready for me to move on. Okay, so this is now jumping to the next section of the read-along document, which is the section about doing statistical inference. And we don't have a ton of time, so we're not going to get through this all today, but we will pick up wherever we leave off. That's where we're going to pick up when the next session of this workshop convenes next week. Okay, so inference is the process of making statements about a population, but based on a sample. So in a simple case, the sample can mean, or sorry, inference can mean using some sample to estimate the mean of the population from which the sample was taken. Okay, and that is what I've been talking about so far. That's what I mean when I say like we're interested in putting a confidence interval around the population mean of the number of barnacles per square meter on that reef in the Gulf of Mexico. We are taking some sample of data and using that to generate a confidence interval that we are going to apply to the population. Okay, and the way we do that is by utilizing the fact that with the normal distribution, with the central limit theorem, if you have enough data, almost any distribution that data comes from, its mean is going to resemble more and more a normal distribution as the amount of data that goes into calculating the mean increases. So knowing that the mean has a normal distribution, knowing that if we also have to estimate the sample standard deviation, then we're dealing with a t-distribution. We at least know that, hey, this is a well-known distribution that we can reason about. And we can calculate our intervals on the scale of this known distribution and then apply some arithmetic to get back onto the scale of our, of the problem we're working on, the problem or the scale of the population. Okay, so to proceed down that track though, there is the important consideration of, can we rely on the central limit theorem to say that the data come from, that the sample mean comes from something so similar to a normal distribution that we can use the normal distribution or use the t-distribution to generate those probabilities, generate those intervals. Okay. So we have the barnacles per unit area of the sample. I want to produce a histogram QQ plot of the barnacles per unit area. Oh, sorry, that's jumping ahead. I wanted to introduce the QQ plot, which we haven't talked about yet. So generate some data Y, and I'm looking at its histogram. Once again, this is generated from a standard normal distribution. And we shouldn't be surprised that a sample from that distribution has a histogram that doesn't quite look like the density of the population it came from, because again, we're dealing with a sample. But there's another diagnostic plot that we haven't looked at yet that can help us determine if our data came from a normal distribution, and that is the QQ plot. And as we go forward, as we're doing inference, as we're trying to assess if something, as we're trying to assess what methods to use to analyze some data, you're going to spend a lot of time looking at QQ plots, because these are a really slick way to say like, oh yeah, this data comes from a normal distribution, or no, this data does not come from a normal distribution. And that can make the difference between saying, oh yeah, we're able to rely on the approximation of a t-distribution, or that, oh no, there's not enough data to rely on the central limit theorem, and the data does not come from a normal distribution, and therefore we're going to have to use some other, say, resampling methods in order to generate our inferences, our confidence intervals, hypothesis tests, whatever they may be. Okay, so QQ plot, the long story, the TLDR, you can look at a QQ plot and you want to see if the data falls along a straight line. That's going to be an indication that the quantiles of your data align with the quantiles of some normal distribution. Okay, so this QQ plot that I'm showing you is of data that was actually sampled from a normal distribution. So you can see how even in the case where the normal distribution is the truth that was used to generate the data, when I talk about the data or the points falling along a straight line, that's not strict. We're not talking about a straight line you could take out a ruler and hold up to the screen. Talking about we're talking about the broad strokes, like, is it reasonable to look at this and see a straight line drawn through it or not? Okay, so what I'm going to do here is generate a few more QQ plots from actually normal data. So same number of data points. Again, for each of these plots, I'm cycling through. I'm just rerunning the same line of code over and over again. The truth is that these are actually from normal distributions. So you should always be looking at these and saying, yep, that looks fine. That looks like a, that looks like a straight line. These could come from a normal distribution. This one, if I saw it in real data, would probably give me pause, just because there's this strong shape to the tail that says like, oh, the tails of this don't look like the tails of a normal distribution. But all of these are truly coming from a normal distribution. Now, if the data does not come from a normal distribution, what might the QQ plot look like? Well, this is data from an exponential distribution. You see this curved shape. This is enough to say like, oh yeah, this is some distribution that is not normal. So I wouldn't directly apply methods that assume that the data follows a normal distribution. I'll draw a few more examples from that same exponential distribution. And then a t distribution, as we've seen, resembles a normal distribution. But if you look at the QQ plot, you can see that a t distribution has the heavy tails of the t distribution are reflected here in the QQ plot. So it's pretty obvious that the distribution of this data is something that isn't normal. And this, it's not an S shape, but it's like an S shape turned on its side. This is a strong indication of a heavy-tailed data distribution. Anyway, I'm not going to proceed to any new material from there. I just wanted to spend a little bit of time looking at QQ plots, because when you're doing data analysis with real data, if you are going to use a method that relies upon some assumptions about the data being from a normal distribution, you've got to look at the QQ plots to confirm that that's the case. And if it's not the case, then think about a different method that you can use with your data. And what are the methods that rely upon the assumption that your data is from a normal distribution? Well, if you're doing inference about the mean and you want to use a t distribution, if there's a ton of data, like a common rule of thumb is more than 30 observations for a single sample, or for a single variable, then the sample size is large, and the central limit theorem might tell you that, yeah, it's okay to rely on that assumption of normality, even if the QQ plot doesn't look right. But if the sample size is small, say only 10 data points, and the QQ plot says like, no, this data is not from a normal distribution, then we have other methods I'm going to tell you about, that are based upon resampling from your data, just like I showed you before, where we take our original data, generate new samples based on sampling from that data with replacement, and generate a t distribution that is specifically adapted to the data set. And we can use that to do all of the inference. And in fact, you could do that all of the time. You just happen to lose some efficiency. So you might get wider confidence intervals than they need to be. But it's an approach you could just use all of the time. We're going to talk about it next week. It's going to be a ton of fun, but my time here is up. So let's end the recording. I'll stay here. I'll be in chat. You can ask questions about any of the things I have presented here. And yeah, we'll meet back next week at the same time.